So, what is a lab on a chip? Well, a lab on a chip is a analytic or bioanalytic laboratory that is downscaled to the size of a chip, of a small chip-sized object. And you see here a nice illustration of such a device where you try to integrate all functions that are normally happening in a in a laboratory and try to integrate them on a very small microfluidic scale. And they come in many colors and many shapes, and if you Google simply lab on a chip or lab on chip and press show images, you get something that looks like this. And it shows you that lab on a chip is about credit card size formats, either in glass or in plastics. Very often you have a disposable cartridge together with a reader of some kind, a readout system, in the form of arrays, for example, and yeah. They just want to give you an idea of how these kind of things could look like. Often you see like people pipetting things on them. Often there's some kind of optofluidic or some electronic detection scheme attached to it also. What I did is I took one of the leading journals, scientific journals in the field is called Lab on a Chip or Lab on Chip. And I took there all the abstracts of that journal, all the abstracts in August 2012, and I made a word cloud of all the abstracts of all the articles in that journal. So you see, a lab on a chip apparently seems to be a microfluidic device for the optical detection in PDMS for the optical detection of cells using flow or particles of some kind of, these are the kind of the keywords that always come back. And we can have a closer look at these keywords and maybe first look at what kind of applications people are talking about. It's about cancer, cells, cytotoxicity, capturing cells, tissue, analysis, arrays of analysis, sensing, blood, bacterial detection. This is kind of the applications that we can find back in this word cloud. And the technologies behind, we see that, well, of course, it's a device and it involves microfluidics, use droplets and particles, often in an array format. It's a lot going to be about surface and surface effects, optofluidic detection, capture of things. It contains, of course, channels, and you do processes in there. So you get some idea of, the technologies that are going to be laying behind. And if you look at the materials this is made of, such devices, we're going to get back to that. But you see on that PDMS, glass, silicon, electrodes integrated. So this word cloud and these pictures give some idea of what is going on in these years in the academic world. We're also going to see that, for example, the materials we're seeing here are not suited, for example, for commercial applications. So the academic world is going one way, and the commercialization of these devices, there's a very slow pickup in commercialization due to the material systems that are actually not very compatible with cost-efficient large-scale manufacturing. And we're going to get back to that also later in the lecture. And of course, as an engineer, you have to ask yourself, when should I use microfluidics at all? I can do things in a big lab, or I can do things, maybe in another way. When should I use microfluidics? I think there's three main reasons why or when you should consider going to microfluidics or to microscale to do things. The first reason is that your application actually demands that you have a small scale or microscale device. That can be, for example, if you want to monitor something in a place where you don't have place. For example, you want to make an implantable, say a pacemaker or an insulin pump, and implant that in the human body. I mean, there is simply not a lot of place in the human body, so you have to really make, in that case, a micro pump or a microsystem to be able to implement it. Also, another thing is that sometimes the things that you're handling, so say for example you want to handle single cells or viruses or DNA, these objects that you want to handle, they are so small that you need sometimes a small-scale device to be able to handle them properly. Other reasons can be that you want to have a portability of your device, and that you demand the functional integration of many functions, and therefore if your device would be too large, it would be prohibitively large to do things. So these are reasons why the application demands a small size of the device. Another major reason is the increased performance that you can get on the microscale. And then the third reason would be the decrease in cost. But let's first look at the increased performance. We're going to talk about the physical effects on the microscale that are different than those on the macroscale. For example, you're going to see we have very large surface per volume, and you have low inertia, and you have surface effects that are dominating. That means that you can do things differently on the microscale than on the macroscale, and that can be beneficial. You can do things maybe faster, because you can move things fast. Things that have a much lower inertia, so they're easier to move around. You can generate larger spatial gradients. So let me illustrate that. Say, for example, I want to create a large thermal gradient for doing a special chemistry, and I need a gradient of, say, 100 degrees. 100 degrees over a very short distance. So if I have one hand at 0 degrees and the other, this at 0 degrees, this at 100 degrees, and I have a certain spatial temperature gradient, the smaller I bring these together, the higher the gradient. Because in this case I have 100 degrees over 10 centimeters, I have 100 degrees over 1 centimeter. And so if I downscale this to 100 degrees over 10 micrometer, I get a huge thermal gradient there. If I want to create 100 degrees over 10 micrometer and I want to do that on a millimeter scale, that means that I would need to have 0 degrees here and 100 times bigger. I would need to do that 10,000 degrees here to, just to be able to do that on the millimeter scale. So to be able to create this high gradients and still keep my temperatures reasonably low, I need to downscale. That's going to be the same with, for example, electrical fields. You can generate very easily very high electrical field gradients on the microscale, and you'll be able to use that. Another effect is surface effects become dominant, because when you're in a microscale, you're always close to a surface, and you'll be able to make things very small and precise. Let's look at decreased cost. In microfluidics, that can be due to two reasons. It can be due to manufacturing. So if you use, as in other applications, if you make a lot of different devices, like if you make like 100 or 1,000 devices at the same time, of course your cost, the batch manufacturing, so the fact that you can do everything in parallel, going to drive down the per device cost. Also the amount of materials that you're going to use is going to be much cheaper if you make it in a microscale. But in microfluidics, that's not always the driving force. Very often the driving force is not the material cost or the manufacturing, but is the consumables. So if I make a device 10 times smaller in size, the volume is going to be 1,000 times smaller. And for example, in a bioreaction, if I want to do a reaction between, say, a protein and an antibody, and I need to buy those proteins and antibodies, they are hugely expensive. If I can go 1,000 or 1,000,000 times smaller in volume, which is easily possible on a microscale, of course my consumable cost will also go down 1,000 to 1,000,000 times. So often that will be the driving reason why I want to downscale a system. And so these are the three reasons why I want to downscale. And so if my application benefits strongly from one of these, or one of these three reasons, or from a combination of them, then you should consider going to the microscale. If you see no benefit in these three regions, then you should really not go to the microscale. There's no reason in doing that, and you can as well stay in the macroscale and try to do what you wanted to do there.